Hi, welcome to Thermodynamics. This is part 2, and of course, I'm Ms. Bedrosian. We're going to be looking at enthalpy right now, which is delta H equals H products minus H reactants. This is the energy or the heat of the reaction is what we're looking at. So let's take a look at the combustion of hydrogen gas. And we have a little diagram. 2H2 gas plus O2 gas yields 2H2O gas, and the energy levels of the little enthalpy diagram is less than. Delta H is less than 0, so will this be exo or endothermic? Well, this is exothermic because heat is leaving the system. Therefore, delta H will be negative. All right, some things to know about enthalpy. Enthalpy is considered to be an extensive property. Extensive property means that how much you have matters. That will affect the numbers. So how much you use matters. And delta H for the reverse reaction is the opposite. It's the opposite sign. So in other words, what goes in must come out. Da, da, da. And the third one, the third point that you need to know is that it depends on the state. Not like the state of Ohio, but solid, liquid, or gas. So the state of the species can have a different enthalpy or cause different enthalpy numbers. All right, let's get a pretend Bunsen burner. I know it's actually not connected. Let's light it. And let's put a little stand. And we're going to go get a little beaker of fluid, stick it on, and a way to measure that heat. So we'll need a thermometer. Here we go. So we can measure how much heat it takes to raise the thermometer 1 degree. So heat capacity is how much heat it takes to raise 1 gram of a substance 1 degree Celsius. Every substance has its own particular heat capacity. This is known as the specific heat, usually denoted as an S. Specific heat is S. The equation for this is S equals Q over M times delta T. S is the specific heat, of course. Q is the amount of energy coming in or out. It's usually expressed in joules or kilojoules. M is grams of the substance. And of course, delta T is the change in temp. So this is how we start to measure, learn how to measure it. By the way, what's the unit of S? Oh, I'm not telling you. You figure it out. Okay, let's do an example. I'm going to do an example with solar heat. Rocks are sometimes used to store heat in solar-powered homes. The specific heat of the rocks, meaning how much energy it takes to raise it 1 gram 1 degree Celsius, is 0.082 joules per gram Kelvin. How much heat is absorbed by 65.5 kilograms rocks if the temp increases by 12 degrees Celsius? You solve. Pause and try and solve. You can pause again. Here's the equation. Q equals S times M times delta T. If you want some guidance, you can pause after every little bit of instruction. This is a plug and chug. Remember that differences in K and differences in Celsius are the same. So they are interchangeable when it comes to something like this. Here's the final answer. You can pause and check your math to make sure you got that answer. Now let's try switching it around. What temperature change would occur if the rocks emitted 325 kilojoules of heat? Solve. Pause. Here comes the answer. 60.5 degrees Celsius is the answer. See if you can figure out how that happened. There's only one equation, so it's not that complicated. So how do we take these measurements in the lab? Well, this is a coffee cup calorimeter. This is considered to be constant pressure calorimetry because it's open to the atmosphere. It's open to the air pressure. So you dissolve something in water, and the heat gained by the water, by the solution, is considered negative Q of the reaction. So Q of the solution is negative Q reaction. 50 milliliters of 0.100 molar AgNO3 and 50 milliliters of 0.100 molar HCl are mixed. The temp increases from 22.2 degrees Celsius to 23.11 degrees Celsius. You can pause and try and solve. You're going to find the delta H in kilojoules per mole of AgNO3. Assume the combined solution has a mass of 100 grams and a specific heat of 4.18 joules per gram Celsius. So step one, in an equation, you're going to determine the total mass. This one is given to you. You might have to determine it in other questions. So this one is given to you. Step two is you need to find delta T, the temp change. Find the delta T. You can pause at any time and try figuring it out the rest yourself. 3, is the reaction exothermic or endothermic? For that, you're going to see which way the temperature changed. Did it go up? Did it go down? You decide. Step 4, you're going to solve for Q. What is Q in the reaction? You should be doing that. Step 5, please remember that delta H is equal to Q under constant pressure. That's why it says QP. I can't make a subscript. Q under constant pressure. Now solve for kilojoules per mole. And don't forget to put the correct sign. And here comes the answer. Negative 68.0 kilojoules per mole. Always read the question carefully to see what units they want the answer in. But what if you want to ignite something and you're not doing it in solution? You would get this little device. This is called constant volume calorimetry because you're going to put the reaction in a little box. It cannot expand to whatever. This is also called a bomb calorimeter. And you're actually going to ignite something and measure the temperature change. It's a pretty cool device that ignites a sample, but some heat gets absorbed by the wall of the bomb chamber itself. So the thermometer's in the liquid outside the chamber, but some of the heat gets absorbed by the wall of the chamber. So you have to take that into account. You need to take the device itself into account with a heat capacity known as C of the calorimeter. The equation, I'm not even going to do an example. This is not difficult. Q in this case is equal to negative C of the calorimeter times delta T. You just have to take that difference into account. Here's a cartoon on thermodynamics. I can't believe I found one. And this is end of part 2.